In dynamic networks, we must answer, are nodes 2 and 4 in the same group? If not, how do we merge them? Union find solves this with 3 operations. Make set creates single element groups. Find locates an element's group. Union merges 2 groups. Tracing every individual connection to check if 2 nodes are linked means our search takes longer every time the network grows. To keep it efficient, we designate a single representative, or root node, to serve as the identity for every element in that set. To store these relationships, we only need to track one thing for each element: which node sits directly above it in the hierarchy. A simple one-dimensional array is enough to map these parent-child pairs. When we run makeset for our first 4 elements, we initialize them as isolated sets. In the array, every element starts by pointing to itself, meaning each node is its own parent and its own root. In this setup, the array index identifies the specific node, and the value stored at that index tells the system where to move next as it climbs toward the root. Let's create 2 sets by calling union on 1 and 2 and 3 and 4. In our array, node 2's parent value changes to 1, and node 4's parent changes to 3. To identify a set, the find operation follows these array values upward. If we call find on 4, the system sees that 4 points to 3, and since 3 points to itself, the system knows 3 is the root representative. Now, consider what happens if we execute union on 1 and 3. Based on the current array, what will find of 3 return, and how will the structure change? The parent of 3 updates to 1. In the tree view, the entire structure that was headed by 3 now sits underneath node 1, merging all 4 elements into a single hierarchy. We link the root specifically because the root is the only node that represents the entire set. By pointing one root to another, every node in both groups now shares the same ultimate representative. Now we can answer our original question. Are element 2 and element 4 part of the same set? The system runs find on both. Find 2 leads straight to root 1. Find 4 moves to node 3, which now points to 1. Both operations terminate at the same root. Because their representative is the same, the system confirms they are part of the same set. This approach is fast as long as our trees are short. Makeset is instantaneous, but the speed of find and union depends entirely on the height of the tree the computer has to climb. If we keep merging nodes in a straight line, linking 1 to 2, 2 to 3, and so on, we create a skewed tree. Instead of a compact group, we've built a structure that looks like a linked list. Now, running find on the bottom node requires the computer to step through every single element in the set to reach the root. The height of the tree has grown to match the number of elements, making the search slow and inefficient. To handle massive datasets, we can't let these trees grow tall. In the next part, we'll implement 2 optimizations that flatten these structures, making every search and merge nearly instantaneous.